Welcome you all for the next session of the IR spectroscopy. I am Dr. Smriti Dwivedi going to discuss about the IR spectroscopy. In the previous lecture, we have learned about the molecular vibrations, number of fundamental vibrations, how we calculate fundamental vibrations. In this lecture, we are going to discuss the following topics: vibrational frequency, factors influencing vibrational frequency, and the fingerprint region. Now, with the help of vibrational frequency given by the application of Hooke's law. This is the frequency and the formula is 1 upon 2 pi root k by nu, where k is your force constant and nu is reduced mass. Reduced mass is equal to m1 m2 upon m1 plus m2 and k is force constant. If we want to calculate wave number of absorption, the formula becomes 1 upon 2 pi c root k by nu, where c is the velocity of light, k is force constant and mu is reduced mass. This vibrational frequency is very important in the case of infrared spectroscopy. With the help of these vibrational frequency or absorption frequency or wave number of absorption, we can easily determine the given organic compounds whose molecular formula is given. We can establish the structural formula on the basis of vibrational frequency. As we earlier discussed that IR spectroscopy is important to detect the number of functional group present in a given organic compound or different types of functional group present in a given organic compound. Force constant, from this equation vibrational frequency is directly proportional to the force constant k. It means as the force constant increases, vibrational frequency or wave number of absorption increases. Force constant for single bond is 5 into 10 to the power 5 dynes per centimeter. For double bond, it is 2 times, means 10 into 10 to the power 5 dynes per centimeter. For triple bond, it is 15 into 10 to the power 5 dynes per centimeter. With the help of these formula, we are able to calculate the vibrational frequency of any stretching and bending vibration. The vibrational frequency of bond will increase as the strength of the bond increases, as we discussed in our previous slide. It also increases with the reduced mass or reduced mass decreases. If we know frequency and atoms in bond, we can get the value of force constant. So, vibrational frequency occur in the order of single bond. Vibrational frequency of single bond is less than vibrational frequency of double bond, and vibrational frequency of double bond is less than vibrational frequency of the triple bond. Now, with the help of this given example, we are going to calculate the vibrational frequency of CH stretch with a force constant of value is given there. Since in the case of CH, it is bonded by single bond, so we have put the value of K is 5 into 10 to the power 5 dynes per centimeter. Mass of carbon is 12 upon 6.02 in 10 to the power 23, and it will come in grams, and second mass yani mass of hydrogen, it will atomic weight divided by Avogadro's number and we will get this. Mass of each atom can be calculated with the help of this. If we want to calculate mass of carbon, we can put atomic weight of carbon upon Avogadro number. Na is Avogadro number and c is the velocity of light. By putting all these value in this equation like this, we get the vibrational frequency of CH stretching. If we want to calculate the vibrational frequency of C double bond O, what should we do? We have to calculate the mass of carbon atom, mass of oxygen atom. Mass of carbon atom is M1, mass of oxygen atom is M2. We have to put the force constant value K. In place of 5, we have to put 10 into 10 to the power 5 dynes per centimeter, and with the help of these equation we can calculate the vibrational frequency of CO bond. If we want to calculate the vibrational frequency of triple bonded compound like C triple bond N, in the same way you have to calculate the mass of carbon, mass of nitrogen, and then you have to put the value of force constant is 3 times of single bond. It means 15 into 10 to the power 5 dynes per centimeter, and in the same way you are able to calculate the vibrational frequency of single bonded compound, double bonded and triple bonded compounds. Now, in the previous lecture we have learned about the vibration, molecular vibrations and types of molecular vibrations, touching and bending, and in this lecture only we studied how to calculate the vibrational frequency with the help of. Now we are going to discuss the factors influencing vibrational frequency in IR. The value of absorption frequency is shifted if the force constant of a bond changes with its electronic structure. Frequency shifts also takes place on working with the same substance in different states like solids, liquid and in vapor. A substance usually absorbed at higher frequency in vapor state as compared to liquid and solid states. Following factors are responsible for shifting the vibrational frequency from their normal values: coupled vibration, hydrogen bonding and electronic effect. Remember, higher wavelength wave number is equal to higher frequency. If wave number of absorption increases, it means frequency also increases. Let us discuss these factors one by one. Coupled vibration. An isolated CH bond has only one stretching vibrational frequency, whereas in case of methylene groups it has shown two stretching vibrations, one symmetric and other asymmetric. This is because of mechanical interaction or coupling between CH stretching vibrations in CH2 group. As we know, asymmetric vibrations occur at a higher frequencies or wave number than symmetric stretching vibrations. These are known as coupled vibrations because they occur at different frequency than that required for isolated CH stretching. A strong vibrational coupling is observed in carboxylic acid, anhydride in which symmetrical and asymmetrical stretching vibrations appear in the region of 1720 to 1825 per centimeter or centimeter inverse. Now, we are going to discuss the second factors which is responsible to increase or decrease the vibrational frequency is hydrogen bonding. As we know, hydrogen bonding is between the electropositive hydrogen atom and electronegative fluorine, oxygen and nitrogen. As we know, hydrogen bonding is two types, intermolecular hydrogen bonding and intramolecular hydrogen bonding. Hydrogen bonding occur in a system containing a proton donor group and a proton acceptor group. If the s orbital of the proton can effectively overlap the p or pi orbital of acceptor group, the stronger the hydrogen bond, the longer the OH bond and the lower the vibrational frequency. What does it mean? It means, let us take, this is the OH bond, this will make bond with another OH, this is the hydrogen bonding, to make, and then these two are the covalent bond. This oxygen tries to pull hydrogen towards each other, towards there, due to which there is a lengthening or weakening of the bond takes place. It means when bond weakens, it means force constant. When force constant decreases, wave number of absorption or absorption frequency also decreases. It means in case of hydrogen bonded compound, wave number of absorption or absorption frequency decreases because force constant decreases. Like in the case of NH stretching, frequency of amines are also affected by hydrogen bonding as that of the hydroxyl group, but frequency shifts for amines are lesser than that for the hydroxyl compounds. Why? Because nitrogen is less electronegative than oxygen. So, the hydrogen bonding in amines is weaker than that in the hydroxyl compound. Intermolecular hydrogen bonds give rise to broad bands, while intramolecular hydrogen bonds give rise to sharp and well defined bands. As we earlier discussed, hydrogen bonding is two types, inter and intra. We can easily distinguish between the inter and intramolecular hydrogen bonding by dilution. Intramolecular hydrogen bonding remains unaffected on dilution, and as a result absorption band also remains unaffected. It means in the case of intramolecular hydrogen bonded compounds, there is no change in the absorption frequency or wave number, whereas in case of intermolecular hydrogen bonded compounds, bonds are broken on dilution, and as a result there is a decrease in the bonded OH absorption peaks. Now, after hydrogen bonding, we discuss the next effect, which is your electronic effect. Change in the absorption frequency for a particular group takes place when the substituents in the neighborhood that a particular group are changed. It means absorption frequency increases or decreases when their neighboring groups are changed. There are three types of electronic effect we are going to discuss here: inductive effect, mesomeric effect and field effect. Let us discuss one by one. Inductive effect. Inductive effects are two types, plus I effect and minus I effect. The introduction of alkyl group, it means it is a plus I group. It results in the lengthening or weakening of the bond. It means lengthening or weakening of the bond makes the force constant to decrease. When force constant decreases, a lowered wave number of absorption also decreases. Wave number of absorption or frequency of absorption decreases because they are directly proportional to the force constant. Let us compare the wave number of absorption for the following compounds. Formaldehyde, the absorption frequency is 1750 centimeter inverse. In the case of acetaldehyde, 1745 centimeter inverse. In the case of acetone, 1715 centimeter inverse. You have seen as plus I group. In this, there is no plus I group. So, the maximum absorption frequency is 17450, while in the case of acetaldehyde, there is 1 plus I group. In the case of acetone, there is 2 plus I group. So, wave number of absorption frequency decreases. Now, the plus I effect decreases, summarize plus I group decreases wave absorption frequency or wave number of frequency absorption. Now, we are going to discuss the minus I effect on the absorption frequency or wave number of absorption. Introduction of an electronegative atom or group causes minus I effect, which results in the bond strength to increase. Minus I group attracts towards minus I group attracts, it means bond becomes strong, bond becomes strong because it means force constant increases. When force constant increases, absorption frequency increases. Hence, the force constant increases and the wave number of absorption increases. Now, we are going to move the next effect, which is mesomeric effect. Mesomeric effect, just like a conjugation effect, it causes lengthening or weakening of the bond and results in lowering of the absorption frequency. Take the example of this is the benzamide and this is the methyl benzoate. As nitrogen is less electronegative than oxygen atom, the electron pair on nitrogen atom in amide is more labile and participate more in conjugation. While in this case conjugation takes place, but as compared to methyl benzoate, conjugation takes place more in benzamide. As the conjugation increases, absorption frequency decreases in case of the amide. Lengthening or weakening of the bond results the force constant to decrease, and you know that force constant or wave number of absorption is directly proportional to the force constant. This is the next effect, this is your field effect, and this field effect is generally found on those compound which is ortho substituted compound. The lone pair of electrons on two atoms influence each other through the space interaction and change the vibrational frequencies of both the groups. This effect is called field effect, and due to this field effect either increases or either decreases the absorption frequency. It depends on the which condition is there at particular time. Now, with the help of vibrational frequencies factors, we are able to identify the given compounds obtained in the spectra. IR spectra is in the form of the graph where various peaks are observed, and with the help of these peaks we can initially identify the which type of functional group are present, which type of group is adjacent to this compounds. These are the some characteristic absorption frequency of the organic groups. We have to remember this and gone through this absorption frequency, and it is very helpful in determining the structure with the help of these frequency range. First of all, alkanes. For alkanes, CH bond, the frequency range is 2850 to 2970 per centimeter. It is a strong. Alkenes, CH bond, alkene is double bonded compound, but we are going to discuss this is a CH of range 3010 3095 medium. For alkyne CH bond, frequency range is 330 centimeter inverse. For aromatic rings, 3010 to 3100. OH either in monomeric alcohols, in the phenols, hydrogen bonded alcohols, carboxylic acid, hydrogen bonded carboxylic acid. These are the ranges of the frequency which we have to remember. For amines, the range is 330 to 3500 medium. C double bond C for alkenes, this is the range. C double bond C, aromatic ring, this is the range. For C triple bond C alkynes, this is the range. Cn for amines and amides, C triple bond N for nitriles, this is the range. C double bond O for aldehyde, ketones, carboxylic acid and esters. This is the most important peak. With the help of this, we can easily determine the carbonyl groups in the form of aldehyde, ketones or esters we determine. And last is NO2 nitro groups, and this is C single bond O in the case of alcohols, ethers, carboxylic acid and esters. Now, after going through the vibrational frequencies, characteristic frequency ranges, we are now going to discuss the most important part of IR spectroscopy, which is called the fingerprint region. IR spectra is often referred to as the fingerprint region of the molecule. It is the most important function of IR spectroscopy to determine the identity of two compounds. Two identical compounds have exactly the same spectra when run in the same medium under identical condition. The region below 1500 centimeter inverse is rich in very absorption, which are caused by mainly bending vibration and those resulting vibrations of CC, CO and CN bonds. In the spectrum, the number of bending vibrations is usually more than the number of stretching vibration. The region is rich in absorption band and it is called the fingerprint region. Some molecules containing the same functional group show similar absorption above 1500 per centimeter, but their spectra differ in the fingerprint region. The identity of an unknown compounds can also be revealed by comparing its IR spectrum with a set of spectra of known compounds under identical conditions. The fingerprint region can be subdivided into three regions. First is 1500 to 1350 centimeter inverse. Second region is 1350 to 1000 centimeter inverse, and third is below 1000 centimeter inverse. We are going to discuss the importance of these three regions in the next slide. Region 1500 to 1350 centimeter inverse. The appearance of doublet near 1380 centimeter inverse and 1365 centimeter inverse shows the presence of tertiary butyl group in the compound. Gem dimethyl shows a medium band. Gem dimethyl means the same carbon in which 2 methyl group is attached is known as gem dimethyl. This gem dimethyl shows a medium band near 1380 centimeter inverse. Out of the 2 strong bands for nitro compounds, one appears in the fingerprint region near 1350 centimeter inverse. Now, the second region is region 1350 to 1000 centimeter inverse. All classes of compound like alcohols, esters, lactones, acid anhydrides show characteristic absorption in this region due to C single bond O stretching. Primary alcohols form 2 strong band at 1350 1260 centimeter and near 1050 per centimeter. Phenol absorb near 1200 centimeter inverse. Esters show 2 strong band between 1380 to 1050 centimeter inverse. Now, the third region is below 1000 per centimeter. The reason the presence of monosubstitution and also disubstitution at ortho and para position in benzene are detected by most characteristic absorption in this region. A band in the region 750 to 700 per centimeter shows monosubstituted benzene. Deformation at 700 centimeter inverse and 970 to 960 centimeter inverse distinguishes between cis and trans alkene. These are the fingerprint. This region is the fingerprint region and this is the functional group region. The IR spectra is divided into 2 regions, one fingerprint region and functional group region. So, this is the range for the fingerprint region and this is the range for the functional group region. Absorption in this fingerprint region is characteristic of the molecule as a whole. This region finds widespread use for identification purpose by comparison with library spectra. Fingerprint region is important because each different compound produces its own unique pattern of peaks like fingerprint in this region. Once you think you have identified as a known compound, you can compare its IR spectra with that of the known sample of the compound. If all the peaks in the fingerprint region matches, you have identified your compound. Compare the spectra of propane 1-ol and propane 2-ol. Both spectra are quite similar in the functional group region. This is the functional group region. You have seen in this spectra, they are quite similar in the functional group region, but their spectra, their absorption pattern in the fingerprint region are completely different. These are the and this. These are the completely different. So, you can easily identify the compound on the basis of fingerprint region. Fingerprint region, like fingerprint of one person and the another person does not matches in the same way. In the same way the absorption frequency of one compound does not matches with the absorption frequency of other compound unless the compound is same. Same compound runs in the same sample, give the same spectra, but different compounds give different absorption frequency, and we can easily identify the compound with the help of going through the fingerprint region. In this lecture, we studied about the vibrational frequencies. With the help of vibration frequency, we can easily calculate the vibrational frequency with the help of by applying the Hooke's law. Vibrational frequency is very important for determination of the organic compound, and in this lecture we studied about the fingerprint region, which is the important tool for the identification of compound with the help of IR spectroscopy. In this lecture, if you have any queries regarding the functional group fingerprint region, regarding the vibrational frequency and regarding the factors influencing vibrational frequency, you can email at me at this address. Thank you.